it's going to be quite a bit more challenging than the one we had last week, and kind of like night and day. So we need to have a few basic principles of how series and parallel circuits work together in order to understand what we're going to be doing in this lab. And so I'm going to start out with some lecture topics that I won't be covering in the regular lecture, so I'm covering it here because this is the optimum time to do it before we have to do these operations in our lab exercise today. And so let's just review what we have learned so far from previous lectures. In a series circuit, we might have say a battery connected to several resistors. In this example that I have on the board, it would be 3. And our basic principle for series circuits is that you have a total resistance that is the sum total of the individual resistors in the circuit. And so we did that last week. We showed that that was true. And also that the total current is the same as the individual currents through the different resistors, simply because there's nowhere else for the current to go. There's no branch points, and so current in equals current out all the way around the loop. And we can also say that the total voltage from the source is equal to the sum of the voltage drops across each resistor. And so we'll be using that principle in lab today to solve some circuit problems. And we'll also be looking at parallel circuits today, which we also talked about in lecture, but we haven't yet done anything with parallel circuits in lab, I don't think. We did all series last week in lab. And so in a parallel circuit, we showed in lecture that the total equivalent resistance is the 1 over the sum of the reciprocals of the individual resistors, such that the total resistance in a parallel circuit is always less than the smallest resistor in the circuit. And so these are principles that you should internalize, because soon what we're going to be doing is looking at series parallel combination circuits in which we have to apply the right principle at the right time within the circuit to solve the overall problem. And so again, in parallel circuits, we have the same voltage drop across all of the resistors in a parallel network. And because there are branch points, there are places where the current can branch off. We have I total coming in this way, but then it can branch off this way into I1. It can go this way for resistor 2, for I2, and current I3 can go that way. So everywhere where there's a branch point, there's a place where the current can fork off. And so it can go 3 different directions, kind of like a river that breaks into 3 different streams, and then each one goes over the same waterfall. Because of that, the total current that we start out with has to equal the sum of the individual currents which made it up. And so with a total resistance that looks like that, we can simplify that if we just have 2 resistors in our circuit. And so if we just have 2 resistors, which will be the case in one part of the lab at least, then what you can do is say that the total resistance is 1 over the sum of the reciprocals, but then here you can find a lowest common denominator between R1 and R2 by multiplying the first term in the denominator by R2 and the second term in the denominator by R1. And when you do that and collect like terms, you get product divided by the sum. And so that turns out to be a particularly useful result when we are trying to simplify circuits, because a lot of times we'll end up with 2 equivalent resistors in parallel. And so then instead of having to go through, and I hate having to do that, where you do 1 over plus 1 over and then 1 over that, you just do product divided by the sum. And so that works kind of nicely then, and we'll see how we can make that work in this lab. Got a demo here to illustrate the difference between series and parallel. These are live rails here, and so that means that I need to always remember before I change the circuit to unplug it, because I'm basically touching the 120 volts if I were to come into direct contact with it. And so I've been in a hurry before and hooked this thing up wrong, and because I bypassed the fuses here, I blew them out a long time ago, and these are such old fuses I didn't know where to replace them, so I just bypassed them. I succeeded in blowing out the main breaker in the building once doing this, but I wasn't responsible for what happened on Tuesday. And so we see here then, look at this, they're starving for current. These are bulbs that would be much brighter than this, but because they're all in series, the voltage drop across each resistor has been cut down significantly. And so we can see then that in that case, the total resistance would be equal to 3R, where R would be the resistance of a single light bulb. We assume that all the resistors have the same resistance. So in series then, we're just adding them up. And so that's 1 plus 1 plus 1 is 3, 3R. So with 3 times the resistance, that cuts the voltage by a factor of 3, voltage drop across all 3, so it's equally shared. And so here, if this is 120 volts across this whole thing, then 40, 40, and 40 would be but that means that it's not getting the proper power requirement to run, and so it runs dimly. And so we'll be seeing this in lab today. Now, the amount of brightness isn't necessarily directly proportional to how much less current you have, though, because of the way these bulbs work. They're what we call non-ohmic, which means that you might have double the current and it might look 5 times brighter. And there's also a temperature dependence on resistance. And so a little later on in this lab, I'll have you measure the total resistance of the light bulbs and the resistance of each light bulb, and then when it's in a series in a parallel network. And what we'll find is that the cold resistance is different from the hot resistance that you get by measuring the current flow. Once you get current flowing through, the resistance may be bigger by a factor of, well, several multiples. I've seen results as much as a factor of 10 greater. So this is in series then. Now in parallel, we're going to probably have to look really carefully to see this, but I'm going to just alter the circuit slightly. Remember that I turned off the power so I don't electrocute myself here. And then hopefully this is going to work the way that I want it to. And so look real carefully and you might see something. Oh gosh, that's way brighter than I thought. Okay, so we'll but we can see here that this is getting the total amount of power that is necessary to get these light bulbs going, much brighter than before. And so how much less resistance is in this total circuit? Well, we can go back to this relationship. 1 over R1 plus 1 over R2 plus 1 over R3. And each one of these is 1 over R. Then this is 1 over 3 over R, which is R over 3. So in parallel, the total resistance is 1/3 the resistance of any of the individual resistors in the circuit. And when it's in series, it's 3 times the resistance. So that means it's a difference of a factor of 9 here between the resistance when it's in series and parallel. We have the same voltage, 9 times less resistance, therefore 9 times more current. And so that's why it looks so much brighter. There's 9 times more current going through when they were in parallel than when they were in series. And so that works in general. If you have a bunch of resistors in parallel and they're all the same, then it's R divided by the number of resistors that are in parallel. So if you had 5 in parallel, it'd be R over 5. If you have 2 in parallel, then that's just product divided by the sum, so that's R squared over 2R, so that's R over 2. So it's just the number of resistors, it's the resistance of one resistor divided by the number of resistors that are in parallel. And so that's our basic principle there. The next thing I wanted to look at is power. Now we've already seen that power can be thought of as being equal to current times voltage. And so let's just take a look at that relationship for a second, because although we did do a lot of problems with power in Physics 288A, we've got a lot of hungry mouths to feed here with these resistors. And these resistors have to keep having current be delivered to them at a certain rate in order for the device to function properly. And so power is a very important parameter in our circuits equations because it tells us how fast you're feeding those hungry resistors and if it is satisfying the requirement that it needs for proper operation. So we showed before that, well, work we know is Q times delta V. So we learned that from chapter 24. So we can turn that into power by saying the rate at which work is done divided by the time elapsed is equal to the power. And then we'll divide the charge by the time. That'll give us current. So we have power equals current times voltage. But there are equivalent forms for this expression. And so I've written them down here. One of them is I squared R. And the other equivalent form for this power expression is delta V squared over R. Now we get this I squared R one from using Ohm's law and writing delta V as IR. So if we do that and plug it in here, then we get I squared R. And we can get this expression by writing I as delta V over R. And then plugging it in here. And that gives us delta V squared over R. And so let's say that we've got two filaments here. One is a 100-watt filament and one is a 75-watt filament. And let's ask which one has the bigger resistance? Which one do you think would have the bigger resistance? 100 watt? Have bigger resistance than the 75? Some people would think that. I think that's kind of a natural assumption, and it turns out it's the reverse. What relationship would we use to find that if we assume that the voltage coming from the supply is 120? And let's not worry about whether that's AC or not, because what we really talk about when we say 120 is what's called RMS voltage. And RMS voltage is, in terms of power, equivalent to a DC battery that has a 120 volt source. So we can think of this for the purposes of this lab and for this example as being a 120 volt battery, even though it's coming out of the wall. And so which one of these three expressions then is going to give us an expression for the resistance with the least amount of trouble? Expression 1, 2, or 3, do you think?
Give us the most trouble?
Least trouble. We're lazy.
2.
Okay. If we use 2, then what's our current equal to? Can we get it in one step?
So,
Well, we know the voltage, but we don't know the current. What about 3? We know the voltage is 120, and we know the power. So does that make sense then that we use 3? Because 3 then would give us what we want without having to do a separate calculation for the current. We just get it in one step. So R then, R for the, let's say the 75 watt bulb would be 120 volts squared divided by 75. So when we do this, I think we got 144 ohms.
192.
Pardon?
192.
This is 192?
Well, I'll do it again, but yeah. So.
Thank you.
Yeah, 192.
192. Okay, so that's for the 75. Now for the 100, R100 is going to be 120 volts. This is watt here. So we'll write in the units. Squared divided by 100.
And that's 144.
That's the 144. Thank you. 144 ohms. So we can see then that the 100 watt filament has less resistance. And does that make sense? Well, if it has more power, then let's think of it in terms of current times voltage. If it has more power, that means it has to have more current, doesn't it? At the same voltage? But having more current means less resistance. Okay, so a higher wattage bulb has to not hold back the flow as much so that there's more current flowing. Because it's the same voltage in both cases, right? And so this one is keeping the electrons under control better. And so that's why you're not getting as much power. But sometimes you want a brighter bulb, but it burns hotter and it has lower resistance, and so those higher wattage bulbs tend to burn out faster. There is one bulb that's still going, I think, from 1900. And they keep it on because they are afraid if they turn it off, it'll never go back on again. But it's like the record breaker. It's been going for 120 some years. That was a low wattage bulb. And also made out of much more durable materials than today. Today, they want them to burn out faster, so they have to go buy more. Okay, so that's an example then of how to use the power expression in one of its 3 equivalent forms. In some cases, you may have the information you need for all 3, but if you don't, then you can save yourself a little bit of trouble by finding the one that gives you the result with the least amount of extra calculation. And so those are our power expressions. The next thing that I wanted to look at is what happens if you have, and this is very common, that you would have a circuit. Well, here's parallel. We saw that was brighter. Series is dimmer. But let's say you have a circuit that is a combination of series and parallel together. Okay, for example, this one that I have up here. And we can imagine that that's connected around to a power source, a battery. So it could be like this, where the battery's like that, and then it comes around, then through the 8 one, and then through the 4, and then up like this, down like that, and then up and around like that. And so we're not showing the power source, but you can see how A and C could be connected to the positive and negative ends of a battery. And so what we might want to do in this situation then is to think about the two resistors that are in parallel here on the right as being a single resistor. And then how do you get that resistance? Well, because it's 2, we use this so often, it's just product divided by the sum. Okay, and so I could reduce that parallel resistor, 2 resistors, to a single equivalent resistance. And by just doing 6 times 3 is 18, divided by 6 plus 3 is 9. 18 divided by 9 is 2. Okay, and so it's equivalent to a 2 ohm resistor. You could also double check that that resistance is less than the smallest resistor in the parallel circuit, and it is. 2 is smaller than 3. So that doesn't prove that you did it right, but at least it shows that your numbers are in the right ballpark. Okay, and so then once you have those 2 resistors in series, then you can just add them up, because the equivalent resistors in series just add together. And so that would give you the final equivalent resistance. Now if you imagine that this is, say, a 14-volt battery, just to make the numbers easy, then you could say that I total is V total over R total. So that would be 14 volts divided by 14 ohms, or 1 ampere. So this is your general procedure then, is to usually, if this is how the problem is given, you have the circuit elements, and then you need to figure out, let's say, the currents through each of the different parts of the circuit, and the voltage drops. Those would be the kinds of things that you would want to know about. So what you'd start out with then is an R total expression. Then you get I total from that, and then you could figure out how the current splits itself off if it has an opportunity to. For example, here, the current would be 1 amp. Here it would be 1 amp. But then here, it would have a voltage drop that would be the same across both resistors. So that's how we identify that they're in parallel. I mean, they look like they're in parallel, but you can draw the circuit any way you want. You could draw it so that they don't look parallel. You could have it come in like this, then you can have this one do this, and that one do this, and then you could just bring wires back together, and then they wouldn't look like they're in parallel anymore. But the thing that tells you they're in parallel is that we have the same voltage drop across both of them. And so that's the key thing here, is because we have the same voltage drop, then you can say, well, the current in has to equal the current out. And so here we have a current that would be I2 is what they're calling it here. And then you'd have a current going this way, which would be I1. And so from that then, you could figure out, well, if this is a 14-volt battery, then across this first resistor, how many, this is 8 ohms, how many volts are we going to drop across that first resistor? What's V1 going to be? If this is 8 ohms and it's 1 amp through it, it's going to be
6.
the voltage drop across here?
Oh, it's
8, right?
Yeah.
IR, right?
14 minus.
Yeah. And so you have 14 here, and then you have a voltage drop of 8, and so what's your voltage here?
6.
6. So your voltage would be 14 there, 6 there. It's measured between here and ground. Okay? This would be measured between here and ground. It would be the same as measuring across there. Once we get to 6, then what is the voltage drop across this resistor, the 1 amp resistor? Or the 4 ohm 1 amp.
4.
Okay, so that's going to be 4 volts dropped across there, so you're going to go from 6 to 2. And then what's the voltage drop across the last 2?
2.
It's got to be 2 because it's 0 by the time you get to the far side over here. Okay, so this is telling me then that my voltage drop across these two resistors is 2 volts. So 2 volts equals I1 times 6 ohms. So that tells me that I1 is equal to 2/6, or 1/3 amp. And then going across this way, I've got the same 2 volts. It's going to be I2 times 3 ohms. That gives me I2 is equal to 2/3 of an amp. So are those reasonable numbers? Well, one thing that we want to check is, do they add up to the current going in? Okay, so this is I total, this is I1, and this is I2. So they do. 2/3 and 1/3 adds up to 1. And that's what we would expect, because current in has to equal total current out. So we double check that. 1 equals 1/3 plus 2/3. So that's all good. We could also double check that the currents are reasonable in terms of what the resistances are here. Now this resistor is a 6 ohm. This one's a 3 ohm. So if you have the same voltage drop going across both of them, but this is half the resistance, then doesn't that mean this has to be double the current? Does that make sense? If you got the same voltage drop, but half the resistance, then the current has to go up by that factor. So this should be double the current of that. Well, this is 2/3 to 1/3, and the constraint is that it has to add up to the total. So you could actually have done that one in your head, but that's a second way of double checking it, is to just say, I know that this has to be in a 2-to-1 ratio because the resistors are in a 2-to-1 ratio. I know this current has to be higher because the voltage drop across both of them is the same. And so then that allows you to check your result and make sure that I total is equal to I1 plus I2. Any questions about that? Okay, so that's a typical way that you can deal with a series parallel combination circuit. Now in our lab, what we're going to have are light bulbs, and all the resistances are going to be the same. Okay, so Mark has been nice enough to set this up for us so that we've got a parallel and a series configuration here. And so the current is going in here, then it goes through this bulb, then around like that along the diagonal, then through this one, and then back out to ground. So if I turn on the power supply, then I see those bulbs lighting up, but maybe not quite as bright as they would normally be if they had the proper power requirements. Okay. And so now let's take these two and hook them up to these 3 resistors that are all in parallel. Okay, now the way that Mark did this is he just connected the ones that are on one side all together and the ones that are on the other side all together. So then you can just go from any one of these 3 here, I'll choose this one, to any one of these 3 down here, because they're all at the same electric point. And then, I don't know if you noticed how bright they were before, but now they're brighter, because now they're all getting the same source voltage. And here, with these 2, it was being divvied up amongst the 2. Okay, and so in the first part of this lab then, what I'd like you to do is to, and basically what you'll be doing is everything that's in the lab manual for experiment 10. Plus, I'd like you to do these extra things which weren't asked for, but which we all agreed should have been originally put in this lab. And so, to begin with, you can measure the cold resistance of each bulb. You can't measure the resistance when there's current flowing through it, because the way that these meters work is that they when you're measuring the resistance, so there's actually a little battery in here. That sends a current through the resistor, and then it measures that, and then scales it to the resistance by knowing the voltage. So it basically does a voltage over current measurement to get the ohms, the resistance. And so you'll be doing that though with cold bulbs. And then later on, you're going to put these things into the series and the parallel configuration, like you to measure the total resistance of the bulbs. And please disconnect the power supply when you do this. Even you go, oh, the power supply is off, so that shouldn't make any difference. But it does, because then you're putting the power supply as a resistor in series with these, and that'll completely mess up the result. So you have to disconnect the power supply completely when you measure the resistance of these bulbs. So you can measure the resistance individually of each one. If you get something that's quite a bit different, let Mark know, and he'll give you a new bulb, because they should all be about the same resistance, but sometimes some of them are about ready to blow. And when they're almost ready to blow, they're going to start having larger resistances just before they blow. Okay, and so you can measure the resistance just by going from one side to the other in parallel, just the same way that you'd measure voltage, and go from one side to the other when they're in series. Then hook the thing up in series and parallel. Measure the total current. Okay, so we learned how to do this last time. Remember that when you measure the current, it's through these two middle ones. And then you take the power supply, you connect it to one terminal, and then you take the other terminal and connect it to the hot side. So that this is a resistor in series with the other resistors, not in parallel. When you're doing voltage measurements, they're in parallel. Here you want it in series. If you don't get it in series, you get it in parallel, then you've knocked that meter out. Because the resistance for the current meter is very small. And so you're basically shorting the circuit out by running all the current through the meter. And so that blows the fuse. And so then this, in the past, has been the lab where we've blown the most fuses. We've fortunately been able to reduce the current a little bit, so we don't blow as many as we used to. But if something's not working, let us check first if you're not sure. But if it doesn't look like the current is working, it could be that it got blown yesterday and nobody said anything. But please let us know if it gets blown so that it's not a time bomb for the next person. Okay. So once you do that then, once you measure that current, then you can go through and do this calculation for the total resistance, and then compare that to the total resistance you got here. What you're going to find is that this resistance will be way bigger, because this is the cold resistance. This is the hot resistance. So don't expect them to be exactly the same. But this is in addition to what's in experiment 10. So you do all of experiment 10, including the virtual exercises, everything, but then add this in, which is a pretty simple thing to do. But it's, I think, interesting and useful. I think it does ask you to find the resistances, but it doesn't do anything with that. And so what I want you to do is compare the actual resistance to the measured resistance and show that it's non-ohmic, basically, that resistance changes because the temperature changes. We have a temperature dependence on the resistivity of the filament. Okay, so the next thing we'll do in step 2 is we'll have a circuit that looks something like this one. Yeah, it's that one. So this is the one, and I just made some numbers up here. These won't be the same as the numbers as you use in this lab. a lot of what you'll be doing is just a relative comparison of brightnesses of the bulb. But be sure and check in the end part, because in the write-up, there are some specific questions that involve numerical calculations. And I know a lot of times in those end write-up things, it's all qualitative. That's where they ask you to do the calculations in this lab. And so be sure to read that through so you can see which data point, what data you actually do need to gather. A couple of people went all the way through, and then they noticed that at the end, and so then they had to go back through and redo everything. Okay, so in this first example, we're going to have a resistor that's in series with two others that are in parallel. And so that's not too difficult to do here. You have two resistors that just hook up as parallel. And then you'll have another resistor that's in series that you'll connect in the right way. And you can have us double check if you want. What you'll find is that these two bulbs should be a different brightness from this one. And you're going to get more voltage dropped across this bulb. Okay? So if we have more voltage dropped across this bulb, we're going to expect that bulb to be brighter. You're going to have less voltage dropped across these two because the equivalent resistance is only half of the resistance of this one. And so these, you would think maybe would only be half as bright. It turns out they're going to be less than half as bright. Yeah, you have to look carefully to see that they're actually on. But you can always turn this thing up a little. Just don't turn it up too much or you'll blow out the bulbs, which we don't want to do. And so I've done a sample calculation here where let's start out with 15 volts. Let's say that R1, R2, and R3 are equal. So to get our total then, that's going to be R1 plus, and then these two in parallel is going to be product divided by the sum. Okay, so R1, and we're assuming here that R1, R2, and R3 are the same. Not necessarily 1 ohm in your case, but I'm just doing a set of sample calculations to show how you would work with this kind of a circuit. And so this is as much a lecture topic as it is lab, because in lab you're going to be noticing there's more voltage drop here and less voltage drop there, that the currents are smaller. But this calculation is what shows that that must be true. And so to get the total resistance then, we do it as R1 plus, and here you're just going to have R over 2, right? Because there's two resistors in parallel. We already established that if you have two resistors that are equal in parallel, it's R over 2. Okay, and so that means that here you've got 1 plus 1/2 is 3/2 ohm. And so to make the numbers come out nice and neat, I made the voltage source 15 volts. In your case, it's not going to be that. It's not going to be that much at all. That would blow out our bulbs. So you don't want to do that to our bulbs. But just do what it says to do in the lab. But for this calculation, let's just say that that's what happened. And so then we would have, once we have our total, that's what you do first. So you start big and then start working your way in with these circuits. So then you get I total. Once you have R total, that's 3/2 ohms. Then you can get I total. That's delta V total over R total. And so for my example, that's 15 volts divided by 1.5 ohms, or that's 2 times 50 over 3, 15 over 3, or 10 amps. So we have a total current of 10 amps. So that 10 amps is going to go through R1 because there's nowhere else for it to go. But then when we get to R2 and R3, it's going to split off. And so we saw in the last example, if those two resistances were different, as is shown here in this picture, then the currents would be in a 2-to-1 ratio, but they'd add up to I total, which would be 10. In this case, though, they have to be equal because the resistors are equal. And so therefore, if this is 10, each one of these is going to have to be 5. Just common sense. You know, if it splits off and it's the same resistance going either direction, then it's going to have to be half of the current goes this way, half of the current goes that way, because it's splitting off basically. It's forking into two different directions. But you can verify that by looking at the voltage drops. You start out at 15, then you go across R1, which is a 1 ohm resistor, 10 times 1, so that's a 10 volt drop. Everybody see that? 10 volts? So that brings us from 15 to 5. Then we go from 5 to 0 here. And so that means that we have half of the voltage dropped across these two resistors. And so V2 equals V3 equals 5, then I2 equals 5 volts over 1 ohm, and that's the same as I3. So each one, and that's how you calculate it, just to verify that that's true. So that's a series parallel combination circuit. And but when you hook it up, what you're going to find is that these two resistors are going to be dimmer, and this one will be brighter, because the one that has the larger voltage drop across it is going to have the bigger amount of power. Remember, power is V squared over R. In this case, all the R's are the same, right? So if delta V is bigger, then the power is bigger. You can see it goes like the voltage squared, right? So however much voltage drop we have, we square that and we divide by the same value for the resistance in each case. Clearly, we're getting more power when we have more voltage drop. So that comes right from this relationship here. Then in part 3, this is part 2. This over there is kind of an extension of part 1. In part 3, you've got two different circuits to do. One looks like this. We have R1, R2, R3. And so hook that up, compare relative brightnesses of the bulb, do whatever is asked for in that problem. Now in this case, you've got two equivalent resistors in parallel. So if you wanted to figure out the total resistance, you'd add these two up, and then you do product divided by the sum, right? So if we wanted the total resistance here, it would be R over 2 this way, R that way. So it would be product R over 2 times R divided by the sum, which is R over 2 plus R. So that would be R squared over 2 times 3 halves R. And so that would be R over 3. Because this 2 goes down like that, and then this becomes 3 halves R, so the 2's cancel. And so that would be the equivalent resistance. And then the R would be whatever you got from the value of R for this. I don't think that it asks you to do that, but this is how you would do that. And then in the second part of this, you add a fourth resistor. And then I think you're just, in this part, supposed to compare the relative brightnesses. So then you have R1, you have R2, R3, and then R4. Now unfortunately, it doesn't give you a picture. So I think the picture here is important. It's valuable, because otherwise you're just reading a description. R2 and R3 are in series with R1, which is in parallel, and then we add another R4, which is in parallel. What? So just one picture like this is worth 1,000 words. So this is R1, R2, R3, and R4. So if you get to this point and you get kind of stuck, let us know, and we can help you, because we've done this. And there are easy ways to do this, and there are hard ways to do this. But, you know, what I like to do, like with something like this, is I put these two in parallel first. So I get those off to the side, like this. Just have them separate on their own. Then over here, I put these two in series. And then I connect them up so that these two in series have the same positive negative as these two that are in parallel. So I can help you with that if you have any questions. Are there any questions about anything? Okay, let's get started.